this is that portion where I have to... Why do I have to do this every time? Okay. All right. So we are starting chapter 7. And we're not going to spend too much time with it. This is basically figuring out what to do with larger systems. With larger systems, we don't know all of the details. Navier-Stokes is 3 or 4 scales below what we're actually looking at things. We just need some average equations and specifically deal with energy losses that happen on the way. Now, so basically this is, we have finished friction factors, and we're going to just take a look at the macroscopic balances in larger systems. And the relevant chapters are 7.1, 7.2, and 7.4. Now, just to kind of recap of how do we do modeling, we always figure out some control volume that we work on, right? And it could be point by point when we were looking at these velocity and pressure distributions. They're actually point-wise, right? So we have a location, x, y, z, and possibly in time as well. And we're going to find things around that point. But the way we got to that equation was by analyzing some small neighborhood and then kind of shrinking that neighborhood. Right? That's how we actually get the differential equations. So the analysis that is required is differential. However, when we go to the larger system, we can't go point by point anymore. We got to actually do integral forms. We have to integrate. So even if we have differential equations that are valid at certain parts of the system, in order to get something that is summing things up is integration. So we ultimately don't know all of the details that would feed information in all of these point-by-point analysis. And all we know is really what's coming in and what's coming out of the system. And the rest we kind of have to figure out. Right? So again, we normally choose between the two depending on a problem. We also choose the concepts that we want to invoke. And sometimes it's a force concept, right? And sometimes it's energy. And specifically in larger systems, so with mass, for instance, we have conservation law. Right? But for energy is not, it's conserved, but not always in all of the, it can actually change forms. Okay? And it can be lost in a way that it's hard to measure. So we kind of have to just figure out where our losses are. So because of the conversion from one form to the other, that can cause problems in accounting for all of the energy. And also having a closed system is often difficult. So if I'm actually creating my own system, or it's like if it's a car or something of that sort, well, yes, that's relatively closed. I have inlets and outlets that are clear, and I have designed the whole thing so I can control it. But in some surface, that can be difficult, right? So isolating my system in order to be a closed system is difficult. Right? So you can often just look at the control as on the system way, but on the system size, it's going to have constant mass, or you can have a control volume, such as fluid mechanics. You just look at the control volume, and mass is constantly going in and out. You're accounting for it in order to, by looking through the boundaries, like what is going through the boundaries, but its mass is variable and the volume is fixed. So we had a test last night. Can you write down the equations of continuity and motion? Let's see. Just write it down for yourself without looking at any cheat sheets or anything. Try to write it up. Or did you just put your brains on erase last night? Restart and erase. Everybody ready? continuity and motion. So change of mass and change of momentum. Ready to test yourself? Some people still writing. Did you do it right? So change momentum is due to what walks into my volume. So that's momentum rho v that walks in with velocity v. And divergence is sort of collecting it over the boundary of that control volume. These are the changes due to the molecular forces. And then external force action. So this is essentially mass and force balance. Force on certain path can do work. Okay? And we actually haven't looked into equation of mechanical energy, but the way you get the mechanical energy balance is by doing this equation of motion dot v. Okay? So you do, because that's force dot v is actually work that the force does, right? And then a couple of your favorite vector expressions and breaking down those divergence operators and gradient operators and how they combine. You love those, right? Okay. Yeah. So it takes 2 pages in my notes to actually get this. Okay. So when you do this dot v and you rearrange, you get the following soup of vector soup of terms. Okay. Now I'm gonna actually go to the next page and see, can you match them up just without now deriving them? We're not gonna go into deriving that, but it's a vector analysis exercise should you feel like testing yourself. So change in my kinetic energy, this is kinetic energy term, right? Kinetic energy density, is caused by, so I have these 6 terms. Could you figure out, again, take a piece of paper, write this down. Okay. And just by looking at the terms, can you figure out which one is work done by viscous forces, which one is work done by pressure, which one is friction loss, which one is work done by external forces, addition by convection, and reversible conversion of kinetic to internal energy. It's 1.5 pages. It's not terrible. Do method of elimination. Right? External forces must be this one, right? So that's the way to approach these things. So this one is 4. Which one has to be convection? First one, right? We got that right. So this is kinetic energy traveling with velocity v, getting into the volume, so I'm collecting it with diversion, right? So we got 2 down. What would be done? Work done by viscous forces?
Tau.
This tau. Okay. Then the second tau is friction loss.
Yeah.
Must be there. All right, we're good. So then we have the other 2. One is called reversible conversion of kinetic to internal energy, right? And work done by pressure. Work done by pressure, PV, remember? Yeah. So this is just differential form of pressure time. Right. Now this term, if you remember, if fluid is incompressible, this is 0. Okay. If it's actually compressible, it's changing volume, right, at a constant pressure. Okay. So if I'm not changing pressure, but I'm just changing the volume, then I have this reversible conversion of kinetic to internal energy. Right. The method of elimination actually works. So again, I'm not going to ask you to derive this unless you really want to. It's not a big deal. It's just a lot of vector calculus, really. But you start by force balance and you do dot V to get the energy, right? And my force balance is equation of motion. And then you rearrange the terms, and after rearranging, you get this. Again, how can I change kinetic energy? I can add it by convection. We already know that, right? Then my pressure does a certain amount of work. And if I'm changing pressure, right, in the system, that is simply the work of the pressure forces. But there's part of it that can be looked at with pressure leaving constant and the fluid changing its essentially volume and the density. And that's the conversion, and this is the reversible one because I can just keep doing this, right? That is the reversible conversion of kinetic to internal energy. We actually have energy losses in this. Typically the part that I cannot necessarily recover is related to viscous forces. So I have just work done by viscous forces. For instance, I have solid surfaces. And they're essentially doing a certain amount of, they're exerting force on my fluid, and they're doing work. Some of it is lost to friction, so this could be heating my system up. Okay. And then finally, I have work of external forces. Now, if I actually, normally we have macroscopic balance. So we balance mass, momentum, and mechanical energy. And my expression of mass balance is equation of continuity. My expression of momentum balance is equation of motion. And this was the equation of mechanical energy. Now, we are not considering in this course conservation of angular momentum. It is mostly used, so everybody knows when you have a skater, right? And the skater does this, and then when they pull their arms in, they're speeding up. And so that's basically they're changing their moment of inertia, and that's speeding them up. Is that there's no, the force, so the things that are remaining the same, that changes. So that's the angular momentum. We often use that when we actually have solid motion. A piece of something rotating. Right? In fluid mechanics, that's still present. We just don't necessarily look at a piece of something. We have fluid flowing. And one thing that is parallel to this is concept of vorticity, which we kind of skipped this year. And given how much it takes on paper to derive, you're happy that we skipped it. Okay? You don't know that you're happy, but you're happy that you skipped it. Ask somebody who took the course 2 years ago. So in any event, we do actually look at the vorticity of the fluid, but one would have to integrate that vorticity to get the same angular momentum conservation that we looked at a piece of a solid rotating. And we don't do that because fluid is constantly coming in and changing, right? But so again, it's not that it's not looked at all. It's just looked into in a different form. And often we have actually vorticity-free fluid velocity fields, and that can actually lend itself to a whole lot of analysis. So we're not paying a lot of attention to it. Now, these first two, continuity of motion, are conservation laws, and they can be written in a closed macroscopic form. Kinetic energy is not conserved, and there is always going to be this internal friction loss, and the term I already pointed out. So the objective of this lecture is to estimate that loss, especially if you have turbulence in the system, which basically skyrockets these losses. Okay. So, and those terms are a lot of times they're just correlations and estimates because we can't do better than that. We can't do detailed analysis. So let's say that we have a system like this. Okay. So my ins and outs, it's a closed system. I just have one inlet and one outlet. And here I have velocity u1, and it's also so I look at typically at average speed of fluid coming through. And it's in the direction of this vector. This is my direction vector, u1. And here I have velocity coming out at some certain average velocity, and it's in direction u2. Okay. So I might have some work done on this system by surroundings. So if I have any kind of parts rotating, they're doing work on the system. I might add some heat to this system. Okay. Some heat might flow out, and I need to actually balance things. So in this case, we're not going into details of, I have to look at this as a system as a whole. Okay? So quantities that I have are inlet and outlet cross-sectional areas. I have average speed, which is just a scalar at inlet and outlet. So my average velocity at inlet, for instance, is this average speed times that vector u1. Okay. And I have the same term for the for v2 u2. And then I'm also going to term w as average mass rate of flow, so mass flux. And the total mass I have in the system at any time is integral over the volume of rho. So that's m total. Okay. So my mass balance is rather simple. Okay. It's what we've done on that small control volume that I shrank to a point to get continuity equation. I can do the same thing on the large thing. And it's essentially mass flow rate in at inlet minus what comes out at outlet. Okay. So I'm going to call these W's. So it's minus W minus W1. So that's what we refer to as delta W. Okay. So this is my mass balance. So ddt and total is minus delta W. So it's an equivalent of what we've seen on small scale. Now, what about momentum? If I'm looking at the total momentum, it's integral of rho v over my entire volume. Okay. So I would go to the equation of motion and integrate it. So if I integrated the ddt rho v, I can exchange integration in ddt terms and get the ddt of my total momentum is essentially convection, what flows in and out. So when I integrate, I will get this. When I integrate the pressure, so let me just flash that equation once again. So this is the equation that I'm integrating, right? And there's essentially a theorem that relates integral of divergence of anything versus that's something that is coming normal to the boundaries through surface integrals, right? And in this case, since most of the surfaces are closed other than inlet and outlet, okay, then the only place for things to go in and out, or this is my boundaries essentially, that are open to the flow. So I have my average of V1 squared S1 U1 minus, the only thing is that I have V squared here. Then I have the pressure term. Okay. So pressure exerted again on those inlets and outlets. This is area of the inlet, outlet. This is the total force that solids in the system, solid boundaries, are exerting on the fluid. We know how to do it. This is integral of tau, right? And then when I integrate rho v term, I get m total. So this is basically the net rate, now that I integrate, of momentum by convection, net pressure force on inlet and outlet, or action of the pressure force, total force of solid surface on fluid. And the reason why I'm putting this in caps in our exercises so far, we were typically busy calculating what is the force of fluid on solid. So this is just the negative of that. Remember those plus minuses and okay. And total external force acting on fluid. Okay. So now we have to, there's just like an alternative equation that I derived, so that's a little more computable. My problem here is this average V squared, okay? So this is, I can write it as rho Vs and then divide by that V. Note that I can't just directly divide this. Average means integration. Integration of V squared over the volume is not the same as square of integration of V. Okay. So this is integral of V, this is integral of V squared. Integral of V squared is not square of the integral of V. It'd be nice, but it's not. Okay. So then I can express also this when I use these terms as delta. Delta means I have 2 minus 1 is my delta, right? So outlet minus inlet, and it's minus because I actually have inlet minus outlet here. So minus delta of this W, which is mass rate, and then this average of V squared over V and U. And this delta is acting on the entire P, S, and U. Technically, I should have brackets.
U is the velocity vector.
Yeah, it's U1 and U2 are just those vectors that are orthogonal to inlet and outlet areas.
Okay,
yeah, normal vectors.
Yeah, normal vectors.
Yes.
Okay.
So they're just unit vectors. Right here.
Yeah.
Okay. So then an alternative way to write this is minus delta W again is mass rate, average of V squared divided by average of V, plus pressure times surface U. And what I mean by delta again is this term evaluated at outlet minus this term evaluated at inlet. Plus force exerted by solid on the fluid. If I have a cylindrical tube, what is this force?
0 minus the
Delta in pressure times
the cross-sectional area.
cross-sectional area, which is R squared P for for a cylindrical. Alright. So, of course, we do the shortcut even if it's not valid. You could just, even if you make a mistake here, you can blame it on the friction losses and the and inability to correctly identify force of the solid and fluids for a complex system. Okay. So often this is done because, again, I'm measuring velocity, I'm measuring only on the inlets and outlets, and I'm measuring average velocity, right? So there's no way to know the average v square everywhere, okay? So at steady state, when I don't have changes in time, then this force of the solid and fluid, which is negative, so force of fluid on solid, which is negative of force on solid and fluid, is equal all this. Okay. And for flow in pipe, we know what this term is. All right. Now, to get to the macroscopic energy balance, okay, there is a little bit of rewriting of these terms. So this is the kinetic energy balance, but if I'm looking at the total energy balance, I need to incorporate the potential energy as well. And potential energy is what's coming out of this term. Okay? Now, G is a constant, but it can be looked at as a gradient of potential. Okay? So I can define a potential phi that this is gradient of. Okay? So if I have this v dot gradient of something, then I do my favorite vector analysis rearrangement. And I can put some of that into this term to actually have a change in time of the total energy, not just kinetic, but also potential. So this is how it's done. So if we define potential energy per unit mass, then G is simply minus gradient of it. This is typical for any kind of definition of potential, is to put a minus in there. And the origin of that is, again, we know that things flow from larger to smaller as opposed to smaller to larger, and all my coordinate definitions will point from smaller to larger. So this is why we often put a minus in there. Though mathematically, plus or minus doesn't really matter, as long as people agree on something. So then my rho v dot g is rho v dot gradient of a scalar field. And we've done this already, but basically we can express that this term here is divergence of rho v phi minus divergence of rho v times phi. And when we incorporate the equation of continuity into this, I can find that this is minus divergence of rho v phi minus d rho dt phi. And since phi doesn't change in time, I can look at this as derivative of time of both rho times phi, and that's what can go into this term as potential energy.
Is that for the
This is for any fluid. Equation of continuity. This, all I did is equation of continuity. That's valid for any fluid. Gravity is not changing in time. Not in the applications on this Earth that we care about. The gravity could be changing, but that would require moving at speeds that we're not moving. Okay, changing our gravity potential by moving to some different planet. Okay, so we're not doing that. And then basically, that's how I get this term in here. Okay, and we're gonna look at this on Monday.